So we're talking neuropharmacology, and the important thing to understand is receptors, because most of our drugs that we have to talk about are classified by receptors and whether they're an agonist or an antagonist for that receptor. So it's important to remember that antagonist means no and agonist means go. So we have our nervous system, which is divided into the central and peripheral. Central, we're not worried about. It's our control center, and we'll get to that later. But the peripheral is divided into the somatic and the autonomic. So somatic only controls voluntary striated skeletal muscle. And that's our normal neuromuscular junction that we think about with acetylcholine. So anything that's at a voluntary skeletal muscle neuromuscular junction is going to be a cholinergic receptor. More specifically, a cholinergic nicotinic M receptor. That's easy. Where it gets difficult is when we go into the autonomic nervous system. The autonomic nervous system is divided into the sympathetic and the parasympathetic. And what do those do? The easy way that you probably remember it is parasympathetic is rest and digest, and sympathetic is fight or flight. So parasympathetic is cholinergic, meaning that acetylcholine is the neurotransmitter, and sympathetic is predominantly adrenergic. There are a few exceptions to the rule, but that means that epinephrine or norepinephrine are acting as the neurotransmitters within the sympathetic nervous system. This video is going to focus mostly on cholinergics, and then later I will get to the adrenergics. So the cholinergics, those are parasympathetic cholinergic receptors. Now there are cholinergic receptors outside of the parasympathetic nervous system, but inside the parasympathetic nervous system, we're looking at cholinergics as well. And those are all of your receptors in the parasympathetic are going to be cholinergic, meaning acetylcholine is the neurotransmitter. So within that, you have nicotinic N, nicotinic M, and muscarinic. Okay, so what does that mean? That means that acetylcholine is the master key. It's like if you're staying at a hotel, you have a key to your room, and the person across the hall from you has a key to their room. And your key unlocks your room, and their key unlocks their room. But when the maid comes, her key unlocks every room on the hallway. Okay, so acetylcholine is the maid's key. It's the master key for our cholinergic receptors. So acetylcholine will unlock every door on the hallway. It'll unlock the nicotinic N receptors, it'll unlock the nicotinic M receptors, and it will unlock the muscarinic receptors. Now, there are some differences among these receptors. These are my two neuromuscular junctions. This is my nicotinic receptor with my axon terminal, and this is my muscarinic receptor with my axon terminal. You have vesicles in each receptor, or each axon terminal. These are my little vesicles that we talked about in a previous video, and they're all full of acetylcholine. So all here in my muscarinic and here in my nicotinic, these are both full of acetylcholine. But what's different is my receptor. This is my nicotinic receptor. That's my little receptor. And the way that I like to think about the nicotinic receptor is like if you had a tunnel going through a mountain. And at the end of the tunnel, to get through the tunnel, you had a toll gate. And you had to pay the man at the toll gate a certain amount of money to get through the tunnel in the mountain. Now, this is my mountain, but it's really a body cell phospholipid bilayer. This is an intracellular protein, and it is my tunnel. So this is my mountain, my cell wall, and this, the intracellular protein, is my tunnel. And this little guy right here is my receptor. That is the toll gate. So, when acetylcholine binds to this nicotinic receptor, it opens my tunnel and ions flow through. That's an ion channel, a chemically mediated ion channel. Now, when acetylcholine binds to this guy, the muscarinic receptor, he has a little different looking thing. He has an intracellular protein that goes all the way down into the cell. So he's kind of attached all the way into the cell. He's kind of sitting on the surface guarding this little channel. So he's kind of going all the way down in. And when acetylcholine comes here and binds to him, he activates what they call a second messenger protein. So he's not necessarily opening a voltage-gated channel, but he's causing something to happen by activating other proteins. These are what they call G proteins inside the cell, and they're being activated by the muscarinic receptor. But the point is, acetylcholine is our friend for both of these guys. It's gonna activate this receptor. Now remember, just because a receptor is activated does not mean that the physiological function speeds up. The activation of this receptor could cause it to slow down. An example of that would be if this were cardiac tissue, acetylcholine coming in and binding here at a muscarinic receptor on the heart and the parasympathetic nervous system would cause the heart rate to slow down. That's important. Okay, so acetylcholine is the master key. It unlocks both of these receptors. But what's the difference? Their shape's a little different, but that doesn't really make a difference pharmacologically. This is what's important pharmacologically. If I introduce a different substance here, that's going to be a different substance. Can anyone guess what the substance might be? It's nicotine. If I introduce nicotine into this neuromuscular junction, it's going to be activated because this is a nicotinic receptor. If I introduce nicotine into this neuromuscular junction and there's no acetylcholine, my acetylcholine has been broken down. Nothing's going to happen. Because in the absence of acetylcholine, that muscarinic receptor is not going to be activated by nicotine. It's specific to another chemical. Can anyone guess what that is going to be? Muscarine, which is a mushroom toxin. So, my acetylcholine's gone, and I introduce muscarine into this neuromuscular junction. It's going to be activated. It's going to go in here, bind to this receptor, and it's going to cause activation of this cardiac tissue. So that would be a muscarinic agonist. It's activating a muscarinic receptor. If I introduced a muscarinic antagonist and it blocked this receptor, even if the body released acetylcholine, it's not going to activate this tissue. Now, if I introduce muscarine, this mushroom toxin, into my nicotinic receptor, nothing's going to happen because it's specific to nicotine or acetylcholine. Now, the implication for pharmacology with this is that you can alter the acetylcholine, but that's going to affect all your nicotinic and all your muscarinic receptors in the body. So that's not very specific. It's not very selective. If you just introduce something that is more specific and that it alters the muscarinic receptors or it alters the nicotinic or blocks the nicotinic or muscarinic receptors, then it's just going to alter those two. It's not going to affect everything with acetylcholine, so it's more specific. Now, where can you do that? This is my beautiful drawing of the nervous system. It's all represented here. You have your brain and your spinal cord, your central nervous system, and then you have your different types of neurons. The first one, all of this represents the peripheral nervous system. The first is the somatic motor neuron. That leaves, remember, somatic is voluntary striated skeletal muscle. So the somatic motor neuron leaves, and it goes all the way to that striated voluntary skeletal muscle. And what did we say our receptors were? We know what the neurotransmitter is between the somatic neuron and the muscle cell. That's acetylcholine, all day, every day. And we also know, so that's a cholinergic receptor here, located on that striated voluntary skeletal muscle. We also know, because we said it earlier, that these are all going to be cholinergic nicotinic M receptors. M for muscle. So anything, if you introduce a nicotinic agonist into this junction, you're going to cause more profound muscle contractions. So maybe you would use that for something to treat myasthenia gravis. Next, we have, this is representing our parasympathetic nervous system. So in the parasympathetic and the sympathetic, we have what you call a ganglion, which is just a bundle of nerve fibers. So you have this preganglionic nerve that leaves the spinal cord, and it comes down and it synapses with the ganglion. And the ganglion goes on off and reaches the body cell. Say this is a heart cell. And it's going to tell the heart what to do. So, if you want to alter this, you have two opportunities to do it, right? Because we said we don't want to use something that alters the action potential on the axon, because it's just not very selective. So you have two opportunities to alter the neurotransmitter selectively. Here at the pre and post ganglionic synapse, and here at the body cell. Okay, so we said this is a parasympathetic nerve fiber, and it's going down and it's innervating the heart. So these are both cholinergic because they both use acetylcholine as their neurotransmitter. Anywhere that you see a preganglionic and postganglionic neuron synapsing, acetylcholine is the transmitter. So these are all going to be cholinergic. Okay, on to the next one. So the next thing that we see is our sympathetic nerve fiber. So same thing. We have our preganglionic neuron, our postganglionic neuron, our ganglia. Acetylcholine is still the neurotransmitter here. However, here, where the sympathetic fiber synapses, this is our fight or flight fiber, where it synapses with the body cell, it's norepinephrine is our neurotransmitter. One other important thing, in the parasympathetic nervous system, usually the ganglia is located near or inside of the body organ that it's changing or targeting, and sympathetic is usually closer to the spinal cord. So here we still have two opportunities to change the neurotransmitter. This is going to be a cholinergic receptor because it's using acetylcholine. All of our ganglia, all of these pre-post ganglionic synapses use acetylcholine. They're all cholinergic. And here is going to be adrenergic because it's using norepinephrine. The last one is a sympathetic preganglionic neuron, but it directly innervates the adrenal medulla. But it's still viewed as a ganglionic synapse. So this is still acetylcholine here, synapsing in the adrenal medulla, but it's causing the release of epinephrine into the bloodstream, and it acts like a hormone would act. But we can still alter the release of acetylcholine just like we could in these other places, even in our neuromuscular junction up here, because these are all cholinergic. All cholinergic. That's cholinergic. The only one that we see on here that's adrenergic is right here. We're in the sympathetic nervous system where we're releasing norepinephrine. Okay, so the last thing that I want to talk about, this video is way too long, is my heart. Don't break my heart, my achy, breaky heart. So when we talk about sympathetic and parasympathetic innervation, it's important to remember two things, that just because parasympathetic is rest and digest doesn't mean we're downrating the physiological response. So here in the heart we are. So most organs, or a lot of organs in the body, are actually innervated by both, the parasympathetic and the sympathetic. And they have opposing forces at those organs. So this is my heart, and it has parasympathetic innervation. Acetylcholine is the neurotransmitter here. This is a cholinergic receptor on my heart. More specifically, a muscarinic cholinergic receptor. This is my sympathetic innervation to the heart. So acetylcholine is my parasympathetic neurotransmitter here, and epinephrine or norepinephrine is my adrenergic neurotransmitter. So this, when epinephrine is activated on the heart, it's going to cause my heart to speed up and beat faster. When parasympathetic, when acetylcholine works on the heart, it's going to slow the heart rate down. So acetylcholine is going to slow the heart rate, and activation of epinephrine is going to speed up the heart. So I think I did this backwards. This should be up, and that should be down. We're just going to put the arrows going both ways. Okay, so the important thing here, aside from my messed up arrows, is this. If we know that this is a muscarinic receptor, a cholinergic muscarinic receptor. So if I say that I'm going to introduce a cholinergic antagonist to the body, what's going to happen? Because activation of this slows the heart. So if I introduce a cholinergic antagonist, a muscarinic cholinergic, because this is a muscarinic receptor. So if I say I introduce a muscarinic antagonist to the heart, what's going to happen? It's going to speed up the heart rate. So our ideal drug, or our normal drug that we talk about with the muscarinic antagonist, is atropine. So when you introduce atropine to the body, you're trying to raise the heart rate. So you're blocking the muscarinic receptor here that causes the heart rate to slow down. Anybody else tired?